Welcome back to Tech Junior Tutorials. My name is Lee Warwick Jr. and we are doing Advent of Code. Today we're going to be talking about day 18. It is the 22nd, so still behind. But day 18 has been an absolute monster. So let's jump in and take a look at it. So here we are on the site. Day 18 is the many worlds interpretation. So they say you get nabbed by some tractor beam, and then you are pulled into some kind of maze. And so they give you these little examples to maybe instill some false confidence, and then it quickly balloons into something much meaner. So if we look at the actual puzzle input, without reading all of this, here is the actual maze that we're going to be working with. So we're going to start right here in the middle, where this @ symbol is, and basically the goal is to collect all of the keys, which are lower letters. So we've had some pathfinding and mazes and stuff before. There's actually another one coming around that's looks to be pretty rough also in the days ahead, I think on day 20. But this one has been a real monster. So I mentioned in the last video, this fellow has some awesome scatter plots, Maritz VD Shi. And what these are is like the average completion times for these puzzles. So if you look, this year hasn't been too bad. Looks like there's been some outliers with like day 7 and 10. But when you get to 16 part 2 is the other one that was kind of rough. But when you get to 18, like not only does part 1 take the top 100 people like maybe 45 minutes to an hour, part 2 took them like almost twice as long. So it looks like day 22 is going to be pretty rough, part 2 at least, but 18 I think on average looks to be the toughest one so far. So I'm hoping to be able to knock these other ones out and catch up. But let's talk about why day 18 was actually so difficult. So they give you some examples and they say your goal is to find how many steps it takes, or the least amount of steps it takes, to gather all the keys. So in this example up here, they say like, all right, your only choice is to grab key A, because the uppercase letters are doors. And so in order to open a door, you have to have the corresponding key. So in order to get key B, you have to get key A first. So that means you got to take 1, 2, 3, 4, 5, 6, 7, 8 steps in order to get both keys. And that is the fewest amount, but also like the only path there is to collect the keys, unless you did something like went there first. So not totally complex, but they give you some other examples. This one's also very linear, where you can only collect seemingly one key at a time. Here you can get C, and then you have a choice of E or D. So looking here, they kind of throw this like real monkey wrench in the whole thing, where they say you've got a choice between keys D and E, and while E is closer, so there's fewer steps to E than there is to D, in the long run, collecting D amounts to more steps. So what that means is you can't just look at all the keys and see like the shortest path to each one and add those together or anything like that, because there's doors in the way. Those doors mean that you're going to eventually run into a situation where you need to bypass a door somewhere else on the map, and you need the key for that. So you end up with this problem of having to calculate all these different combinations of steps, or of different keys that you can get in like what order. So this one's a really good example of it. Like how do you know which one to get first, and like how do you write an algorithm to prioritize one key over the other? If here we've got 4 keys that are all basically equidistant from each other, and then 4 doors equidistant, another set that's just as far. So these like doors and keys are all over the place, and coding for this like intelligently is a real nightmare. So it'd be a really tough algorithm to write, I think, to do this without like a lot of basically iterations and loops over the data set. So I wasn't able to do that. I had a lot of struggle with this one. Here's another little example they give that's like, okay, here's 3 doors and a door here, and then like a set of keys and a set of keys. You know, do you go this way or do you come down? Or so there's a lot of complexity to the problem. And then, like I said before, if we look at the actual input that they give you, it's like this massive map. It's absolutely huge. So you can imagine like the amount of combinations of pathways that you could take to get to any different point on the map is immense. So this ended up being a problem of not only like, what the heck is the algorithm that I'm looking for? What is the actual problem that I'm trying to solve? But also like, how do I do it in a reasonable amount of time where my computer won't run out of memory trying to crunch the numbers on this? So if we look at the problem set again, basically what I ended up doing was I grabbed my previous algorithm from day 15 where we had another maze, and I tried to use that for my pathfinding to find like the distance to each key. But the problem was that if we look at the actual input, if you look at the middle of the maze, like right here, there's like a 3x3 open square of space. So every other point on this map is a hallway, but right here in the middle, there's a big open room basically. And so what my algorithm was doing was it would like circle this point here, take some kind of like crazy path to go find a key. So it would be a couple of steps off for everything. So like right off the bat, I was kind of sunk. I spent a lot of time porting that code over and removing like the encode stuff for it to try and get it to run on this. And then I ended up talking to some people from Orlando Developers Group, and one of them told me that his algorithm that he was using was like a flood algorithm. So back on day 15, they had this question, or I'm sorry, was it day 15? I think 15.2, where they're talking about flooding the maze with oxygen after finding the oxygen tank. What I had done was I just found the longest path and figured like, okay, if I find the longest path, that's going to be the amount of steps that it takes to fill the maze with oxygen. But for this, you could also use that same kind of algorithm of like flooding the map basically to figure out like the shortest path by saying like, okay, if this is a path, then I can take this path and compare the two and see which one's faster. And if they're the same, only grab one of them. So I ended up having to refactor. I used that algorithm. I did use some of my code from the previous day, so that was nice. But the real problem was like, how do you figure out what order to get the keys in? And so the kind of naive solution is find all of the possible combinations. So that's what I did at first, which is basically, so like for this example, they give you one, they say like, oh, here's one of the shortest paths. Basically to find all the combinations of these that are possible and compare how many steps it takes. But whenever you get into something like that, where here we've got like, I think 16 keys, you've got like this factorial times factorial problem where all of a sudden you're looking at like in the tens of millions of combinations. And so crunching those numbers on your processor becomes more and more memory intensive until basically you bottleneck and it never runs it. So you have to somehow optimize that so that it finishes faster. And so I went through a couple of different attempts to figure out what I could, like, what information I could discard So obviously, like once you pick up a couple of these keys, I was thinking there's got to be some of those different pathways that you can get rid of. So like if you go from A to F and that's shorter than starting with F and going to B or something like that, I was like, okay, well maybe I can trim the bottom half of the list or something. So if I've got at any given point like 100 different paths or 1,000,000 different paths or something like that, take the back half of that that has like the highest amount of step count at that point and just get rid of them. Who cares? Or if I have more than 10 million paths that I'm tracking at any given time, limit it to that or something and get rid of the rest of them. And so that would work on some of these examples, like the small one. I could limit it to like 1,000 or something and it would give me 132. But for this one in particular, the second example, you can see there's a lot of different pathways that you could go and a lot of different keys that you can grab. The complexity of this one is such that you get that many, many millions of possibilities. And so I would still bottleneck, or it would cut out what was actually the answer. And so I would get like 144 steps if I cut out like 1,000 or 1,000,000 or something like that. So I started to think like, well, what if I can cache the paths that I'm taking by like, okay, let's say I have a set of 5 keys. Why don't I consider that a state? And then any combination of those. So if I get, 5 keys in and I look and I have the same keys, the same 5 keys, take the lowest one basically and just get rid of the rest. And so that was really close to what I really needed at the end of the day, but didn't actually cut the mustard. So that worked for actually, I think, all of the examples on the page, but it did not work for the actual input data. So I spent a couple of days on this, a couple of late nights, really beating my head against the desk, trying to figure out what the heck am I missing. I started reading the Reddit, so you can go on like Advent of Code Day 18 solutions and jump on here and start reading. And if you look at some of the code on here, it is let me see if I can find like a Python solution or something. I don't know. Let's look at this one. So you look at this code and you're like, what is this? So obviously this person has done it in like maybe 50 lines or something, or maybe 100. And you just look at this and it's uncommented. They obviously were like doing this for speed. You're like, wow, I don't know what this is. This doesn't help. So even like cheating, basically reading all of these and seeing like, okay, they're using a Dijkstra algorithm or a breadth first search or a depth first search. Like I went and looked those up. I looked up Dijkstra's algorithm. I looked up breadth first and depth first. I realized that what I was doing essentially was a breadth first search. So I was looking at like all the possible combinations and then trying to like pare it down from there instead of going all the way to the end. I actually did try depth first because I read on here somebody was like, oh, I use DFS, and that got it done. So I tried to like create one solid path and then work backwards and try and like flip the keys or find the other keys from that. I ended up scrapping that. So I ended up rewriting this code like many, many times before I actually landed on what actually was the solution. But one runaway comment in here was like, oh, you have to keep track of the previous states and then get rid of whatever states have less steps, which was really, really close to what I was doing before. And basically, the key that I was missing, not to use a bad pun, was that going back to the code here. Let's say that we had A, F, B, and J at any given point, like we were calculating all these different possibilities of keys to grab. If you've got A, F, B, J, and then you have like BFAJ or something, or FABJ, and those all have different step counts. If you've collected let's say these three keys in whatever combination, and now you have key J, that is the same state as if you had collected these first three keys in any different order. So if you end up with the same keys plus the same ending key or current key that you're on, that's the same state as another possibility with those same keys. So if you take all of those and you get rid of the ones that have the greater amount of steps, you can throw away a ton of possible combinations. So without doing that, you quickly get into an order of magnitude that's like tens of millions. So it goes from like 64, 500, 2,000, and I know this because I printed them out, but 50,000 up to like 1 million, and I think about 1 million doing like nested for loops is where my processor says I'm throwing in the towel. So when you do this optimization, you can cut those numbers down to the thousands, which makes this run a heck of a lot faster. So let's go ahead and check out the code that I used to get there. This is going to be very confusing, so if you've listened to what I said now and you're trying these at home, that's going to be what's going to get you there. Looking at my code really isn't, but it's kind of neat, so let's talk about it. And just for reference, the actual input was 5964, so before I was getting numbers in like I think 6090 was my first guess, and that was with just like trimming the top half of the list. So there was like about 50 steps that were really getting me down there. So anyway, looking at my code here. So this code is a little bit longer too because I've put in a lot of stuff to visualize this pathfinding and whatnot. So the first thing I do is I get my input. I've got a couple of other different test cases in here from the examples on the page. So that's why this is like input 3. So I go ahead and open the file. I parse it into a grid of XY coordinates with these nested for loops. So basically I split the file into lines, and then for each line, I iterate over each character in the line and determine like, is it a free space, is it a wall, or is it the origin? And then for the doors and the keys, I use something I learned from day 16, I think, or 17, which is Ascii characters in Python. So I look at if the character is basically a letter. So this is, I think, uppercase letters for the doors, and this is lowercase letters. So if it's an uppercase letter, that means you've hit a door. Go ahead and store that in a dictionary with the point first. So I've got a couple of helper functions, like to turn each coordinate into a string so that I can easily put it into a set and like dedupe it and keep track of it very easily and look it up really quickly. I do that for doors and keys, and then create the maze. And then I grab like the height and width of the maze, which I don't even know if I use that anywhere, but a lot of stuff to just visualize this. So then I use the same MazeBot class that I was using from day 15, because I ported that code over here and started refactoring it to see if that algorithm would work, which it didn't. I refactored my get surrounding coordinates method. So what this does is basically for any given coordinate, if you give it a set of coordinates that you've already visited, it will tell you for that position what's around it. So it'll look up, down, left, and right and see like, okay, is that thing in the paths? Is it a wall, or is it unexplored territory? I've got a whole method to print my grid, and this just like loops over the walls and the doors and the keys and the current places that I visited and visualizes that. And then it will clear the screen and like animate this on the terminal basically. So that code is kind of worthless for the solution, but it's really neat to look at. So I kept it in there. It also helped for debugging, especially that case where I was looking at the middle here, And if I visualized and actually printed the path that I was taking, I could see like, oh my gosh, I was swirling around this empty room and then going and exploring one of these coordinates. So, or quadrants. So, that was actually helpful to visualize the actual maze. And then my algorithm to search and pathfind is I've deemed it flood, and I used to have it as like explore was the other one. But flood basically is going to, whenever it hits a branch, spawn a new path and just start going down that pathway or hallway until it hits a new fork, and then split again until it hits a dead end, and then it stops. So I've got a while loop, and then I've got my different paths, and then key paths, and a count. I believe the count is okay. Yeah, so I'm using that for keys in the paths dictionary, just so I can do a quick lookup in there. And also it helped me like realize how many paths I'm generating whenever I'm like flooding the grid or the maze with different directions that I'm searching in, basically. So going through there, I do this while loop where it's funny, I don't actually flip exploring to false, I just break. But so I loop over these paths that I create. So I look at the position that I'm in and the surrounding coordinates, and then for every unexplored surrounding coordinate, generate a new path, and then loop over those paths, and then I get the places I've already visited, any doors that I've hit along the way, and then my current position in the list of coordinates that I've been in. And then I first check to see if I've hit a key, and then store that if I have in the key paths dictionary. If I've hit a door, add that to the doors set that I'm passing along in each iteration. And then I basically create a new paths dictionary for each iteration through of this path dictionary. So again, this code is very messy, and all these loops and stuff I'm sure are terrible. But this was how I could think about it, and just kind of like a naive implementation of this search algorithm. And then I've got like some printing code here, the same as this. So I'm coding this as a class, but I don't actually use too many private variables or internal variables for that class. Most of this stuff is functional. But I loop through all that, and then at the end, I look at all of my key paths and then kind of like munge them into a dictionary of paths where I've got like the distance, the doors, and the location of the key that I've hit. So from a point, I'm finding how far to a key, or how far to all keys, basically, how many doors you pass along the way to get there, and what is the location of that key when you hit it. I was passing along paths themselves and like getting all the coordinates and just passing them back. I didn't actually need that, so I just kind of commented it out. So if you're still with me, from there I've got another method, which is get keys. So that is going to call the previous two things we talked about. So it's going to get all of the keys, or the distance to the keys, from the middle of the map. And then it's going to look at the distance from each key to each other key. So I get all the keys, then I loop through that, and then I call flood again on that position. So for each key that I find, call it again to find the distance to the other keys. So I'm basically exploring the map once for the origin, and then one time for each key on the map. And that all that data is then like cached, and I don't have to explore the map again from there, because I only care about the distance, the total amount of steps to collect all the keys. So I do this another while loop very similar to the one from the flood method, where I create a new bunch of paths. So every time that I'm kind of branching, instead of branching from hallways, I'm branching from key to key. So I start with the original keys from the origin, and then I basically create a new path for every possible key from there. So just to kind of put a spin on this visually. So I say like, okay, I'm going to get C, E, B, F, A, G, D, H. And then I'm going to get from B, J, and O, and F, and E. So I'm going to look at all those distances, and then I'm going to say, okay, if I get B, that's a path. Make a path for C, make a path for E, iterate over all of those, and then say like, okay, from B, I can go to F, I can go to E, I can go to C, I can go to A, G, N, because there's a B door right there, D, and H. And then from there, from each one of those keys, okay, let's say I can go to B, and then I can go to D, I can go to H, and C, and G, and N, and E, so on and so forth. So it's like a, if Dijkstra's algorithm is like going over a graph and going from point to point and finding the shortest path between one point and another point, that's like, I'm doing kind of like one for the maze itself, where I'm finding like all the pathways and the shortest pathway to like that key. But then I'm doing from like key to key. So it's like a double Dijkstra's algorithm, which is kind of crazy. But even though this isn't like the most elegant Python or beautiful Python or whatever, it does work. So let's actually run some of this and see what this looks like. So what do we have for input? So input 3 is this example from the Advent of Code page, this one. So when we run this, you'll see pretty quickly like what is going on. So let's go ahead and run this, and you can see it is going to jump to each key and explore the map, right? So you could see the @ symbol was like the current location. So it runs from each key location to every other key location, and then it starts comparing all of those. And so with my optimization, remember we talked about storing the different states, right? So basically that is in, where are we at? This is the flood method. So thank goodness for VS Code's collapsing methods. We're going to look at get keys. So here's the cached bit that I was talking about. So whenever I loop through each different possible paths, so from like this key to that key, means I can go from this key to these 6 keys, and then from those 6 keys I can go to these 5 keys a piece. It exponentially becomes huge. That's that factorial thing that I was talking about earlier. So I do the check where I look like, okay, for my set of keys, which I'm storing as a string, and then exploding that out into a set. So I've got a lowercase path. So like this is my keys, right? And so I explode that out to a set. It gives me a set of keys. I do the same thing for pass doors, or passable doors. So I look up for any other given key. I say like, okay, if that door is not in passable doors, then you can't get that key. So don't continue on from there. So that cuts down a little bit. But the real the real optimization is here. So what I'm doing is now I'm taking the path. So you notice these are in alphabetical order. I'm taking the path turning it into a list, sorting the list, and then joining that into a string plus the current state that I'm at, or the current key that I'm at. So I alphabetize the first grouping of keys because I'm storing these things in a dictionary. And then I'm doing a comparison and saying like, hey, if that state is already in the possible paths that I've generated, check to see if I've got a smaller distance now, and if I do, replace that. Or if I don't have that state, go ahead and save that current state. Basically, if I don't do that, these amount of paths here explodes exponentially. So I don't know if I can get this to run. Because I've refactored this, but basically before these numbers were exponentially higher. So for this this problem, the numbers would be like in the hundreds, but for something like this one, the numbers quickly creeped up into the millions. And so now, if we run this maze, so we're going to look at example 2, you can see it's going to jump and kind of explode out from each thing. Now you can see we cap out at like 6,000 possible different paths. So I'm only doing like those for loops and stuff over, 6,000 different data points. Whereas before I was in the millions. And so like a nested for loop in the millions takes forever. And then it's only going to get magnitudes of like exponentially bigger from there. So millions becomes like tens of millions before it's actually, you're actually generating all of the possible paths. And then you still have to compare all of those. So you have to loop through all those again and then find the shortest one. So throwing away those extra paths that you don't need really helps to speed this up. So you can see like the pathfinding itself actually takes longer than comparing all of the different possible paths between keys, which is kind of amazing when you think about it. Even if I turn off the printing, you'll see that it's still like that part takes longer. Like the paths don't start coming out until the very end. So 136 for this one. If we look at Advent of Code, there it is. So I've got another example of this we can look at really quick just to look at the pathfinding. So this is going to run a little bit slower. For whatever reason, Git Bash runs a little bit slower than VS Code's version of Git Bash, but this is the blood algorithm that I wrote, going from each key to each other key, basically ending to all points in the map. There we go. Let's actually look at the real puzzle input. So I got a really small font terminal ready for this so we can take a look at it. But let's go ahead and open up the real input. And so I've got this in my print function. I just commented out that if you go and look up at these examples later, I'll have this uncommented, but I filter for input.txt because it's too big for most terminal windows. So, but we'll go ahead and run it real quick. So there is the entire map. You can see this actually takes a couple seconds to run, even when you're not printing it, because it's got to go from the center to all points or all dead ends of the map, basically black out the map, fill every hallway, and then it has to do that for each key to find the distance between each key to every other key. So it doesn't really make for a great GIF because it's so big and it's really hard to see what's going on here, but that is the method that I used for the pathfinding. So we'll cancel that and move on to the actual solution. Yeah, if we actually run this, see how long it takes. We are at 5 seconds. 10 seconds. 15. 20. That's super exciting. Listen to me count. 25. 30. There we go. So about 35 seconds. That's with like all my video running, listening to music, Slack open, Chrome, all that stuff. As you can see here, we've got we start out with 60 possible paths from key to key, or from origin, I guess, to key. From origin to key, and then from key to key. With the doors being closed. So then that quickly jumps up to 228, 598, 1,000, 2,000, 3,000, 4,000. Without that optimization of throwing away the cache states, or comparing the state based on like gathered keys plus final key or most recent key at the end, this quickly ballooned up to like tens of thousands, millions. So by like that cycle through, it was up to like, 20,000, 100,000, 1 million. And so this thing would never finish. I even tried to let it finish, and I got like terminal errors where it was like, you've got a memory problem, and we've run out of memory. So this is all the keys we've collected. This is alphabetized up until the final key. So the final key that you collect is O. I could have gone through and captured the actual path, stored that in there, and then printed that out as well. I didn't really care to go back and play with it that much, but you see the output 5964. If we go back to the puzzle, 5964 is the answer. So I could not tell you how excited I was to actually finally get that to run and complete. It runs a heck of a lot faster off of camera. I know that this is taking up a lot of memory, I'm sure, in the computer, but it maybe runs 15, 20 seconds normally. So some people were talking about on Reddit they could get it in like 10 milliseconds or something. I was just happy that it finished it all. So with that victory and realizing like, okay, I've finally landed on something, I moved on to part 2 and was like, all right, I'm gonna get this thing. So for part 2, now they say like, okay, find this little trouble zone on the map that I was previously so mad at and turn it into this. So now you're gonna have 4 robots traversing the maze instead of 1. So I had thought about that previously anyway, because looking at the map, it already seems like it's divvied up into 4 quadrants. So you've got like a north west, a northeast, a southwest, a southeast. So I had thought about like creating 4 different robots originally and starting them like there and there, filling in a wall, doing pretty much exactly what the puzzle instructions were saying to do. So getting this like wasn't too much worse, but what they want you to do now is say like, you've got 4 robots running at the same time. How many steps can it take if you've got 4 different robots and they collect the keys? But if you look at the input, which I had printed out all this information when I was banging my head against the desk previously, you would see that for the puzzle input, they don't actually put a key within its a door and a key in the same quadrant, basically. The keys and the doors are all in separate quadrants. So like this northwest robot collects this key, but what about this door down here? So what they tell you is that if you collect a key, that instantly unlocks the door. So if this robot gets this key, this robot now has access to B, because A instantly unlocks. So before I was worried about like having to go and like scan this area and then return to the origin, calculate like that filled in spot, add like a couple steps to the path, and then go search another quadrant or something. That would have been a lot more complexity to it. But thankfully they say like, because the door instantly unlocks, you don't have to go back and like hand the key off or anything, which is good. So that means like I can go and run this robot to here, and then run this robot to here, run this robot to here, and so forth, without worrying about handing the keys off or jumping around or whatever. So because I already had my my code coded as a class, it was a lot easier to change this map and then spawn just 4 different robots and run them all kind of at the same time. So the problem is kind of the same, because now you're still figuring out in order to collect the keys, because you can only move, I think, 1 robot at a time. Yeah, they move independently, but you can only remotely control 1 at a time. So that means that while 1 robot is moving, the other robots are stopped. Therefore, the step count is still going to be the same. So like 1 can't be moving while another one is moving, meaning that when 1 goes and grabs a key and you want to control another one, that original one stops and you move on to the second one. So you're still like, even though the map is divided now, the pathfinding like algorithm doesn't change a whole lot, because you still have to figure out like which key do you get when, right? So if you get A and then B, like the only difference now is this wall here, really, and that you've got 4 different current positions to keep track of, kind of. So they've got a couple examples of this. I didn't actually use any of these. I just ran it against the original input. My final answer was 1996. So I'm going to open up that. I did go ahead and copy over a couple of these smaller inputs just for giggles, kind of to animate things and see what would happen. Interestingly, this one I don't get the correct answer, but I do get the correct answer on the main input. So I don't know what edge case that thing has that the puzzle input doesn't, but I'm glad that I didn't hit it, because I was pretty much sick of this problem by the time I got part 2 done. So most of this code is the same. One difference is that now I track programmatically those 4 different quadrants and the origins. So I've made another input file for part 2 where I've filled in the center of the map. And now I'm looking for these at symbols, and I just say like, hey, if my x value is less than half of the width of the map, then that means that I'm on this side, and if my y value is less than half, that means I'm in the top right. I'll do that for all 4 quadrants and track the origin for each one. Then way down here at the bottom, basically I create a new function called getKeys, and then for each robot now, I'm going to spawn a new MazeBot class using that origin point. And then from there, I've refactored my getKeys and paths. Before, this was kind of doing the whole kit and caboodle. It was doing like, give me the original distances, give me the distance between the keys, and then crunch all the numbers and spit out the solution. I basically refactored it to only spit out those first 2 things, which is the original key distances, the distances between those keys, and the starting paths. So that's what it returns as a tuple. And then my flood algorithm is the same. need to move this. So I suspect that looping over these paths is a little inefficient. So I'm going to drop that there. And this is just for visualizing the puzzle, so. Oops. Otherwise, the flood algorithm is the same. Don't need to worry about that. Print is pretty much the same. Get surrounding coordinates is the same. My init is the same. So I loop over, or basically explore all 4 quadrants. Let's see if we can visualize that. So looking at input part 2, I want to look at input part 2, example 2, which is this one. To run that, you can see I explore each quadrant at a time, and then I get 32 steps minimum. Which is, I think, this one here. Which is good, but this one, things fall apart, which I'm not entirely sure why. I get to 74 instead of 72, but... so what I do for part 2 that's different is instead of looping over the one set of distances between keys, that dictionary, I'm looping over 4 of them now. And I'm saying like, all right, for each, first I munge all this data, right? I create a bunch of initial paths and I put that in a paths dictionary. And for each path that I create, I get the current distance. And then what I do now is I store the last key in each quadrant. And then I say, let's say I'm looking in the southeast quadrant at any given point. If I'm looking for a possible path and or a possible next key, and that thing's in the southeast quadrant, if I have a string of keys there, go ahead and grab the last one from that, and that would be the last key that I've grabbed. So that's like my way to keep track of the current state. I've still got all the current keys smashed together as a alphabetized thing with the, or string with the last letter being the last key collected. But this helps me figure out like which section or quadrant to look in, as well as keep track of like what the next possible key I can collect is. So I loop over that. I basically added a for loop to my logic here, where now I say like, okay, grab the last key from the paths dictionary and loop over the dictionary of key distances for that quadrant. If it's none, I need to grab the original dictionary, because if it is none, that means that the robot's still in the origin spot. So I've got that handled as well. And then I'm still caching everything. I just had to add a couple of lines that basically loops through the quadrants and adds in the last key for each quadrant. So like the path data grew a little bit, but the algorithm is pretty much the same. So let's go ahead and run this for the main puzzle and see what we get. This may take a few seconds. It's a lot faster. So exploring the maze in quadrants is a heck of a lot faster, and so you notice like the algorithm is super fast. That flood algorithm is not very good, so it was easier to just like wait the extra 10 seconds than to refactor that into something like a lot faster. But you can see this one, we're not even getting up into the 6,000 possible paths here. We're getting like max 4,000. But then we get 96, or 1996 is the answer. And with W as the last key that we're collecting. And the answer is indeed 1996. Where this falls apart is that edge case that pops up in the last example they have, which is this one we're looking at. This one here. So you look at that one, you can see it explores each quadrant at a time. But then I get 74. So there's an edge case in there. I don't know what it is. I'm not going to find it. I don't care what it is at this point because I solved the puzzle. Maybe their input's wrong. I don't know. Probably not. It's probably something wrong with the puzzle or with my algorithm. But I'm glad whatever edge case is in there didn't show up in the input because that would be maddening. I've already spent many hours on this puzzle, and I do not wish to spend any more on it. So yeah, that is all I've got for day 18. Looking ahead, day 19 doesn't look too bad. It's dealing with the tractor beam. It's running on int code. Day 20 is another puzzle where you've got to like start at A and then find a path, the shortest path basically to Z. And then these BCs are portals. So BC goes to BC, kind of like, it's like a donut shaped maze where you go to BC, if you're here, you go down, you'll pop out here. And that is like the exact input that they give you. So even parsing this is going to be a pain in the butt because like you've got to somehow parse these points, which kind of stinks. Even like HL, you've got an IH here. So you can't even look like right outside the bounds of the maze to figure it out. So that one will probably be pretty dang difficult to get through. I think I can get it done with the same kind of stuff that I was doing for today's challenge, but it remains to be seen. If we look back at Morit's visualization for this, it's definitely not as hard as today's. So hopefully I'll be able to get that one done. But then day 22 looks pretty rough. I think 19 and 21 are int code problems. So those typically haven't been that bad once we've gotten the thing solved, gotten the final int code computer running. But yeah, day 22 looks a little scary. But yeah, that's all I've got for this one. This has been a really long video, so I apologize for that. But yeah, let me know how you're doing with these. Day 18 has been an absolute nightmare. A lot of people that were doing this with me have gotten hung up on that one and basically said like, I'm done spending time on this. I'm pumping the brakes. I need to go do other things. I can't sit here and solve this dang maze. I know I certainly cussed it a little bit, but I'm really happy that I finally nailed it. It really bothers me to not give up on these things, or if I had to give up on it, it would really bother me. So it's like a nagging, like, oh man, could you really not get that? Or could you have gotten it if you spent a little bit more time on it, or were you right there or something? So I'm glad that I finally got it, but certainly can't keep spending that much time on these puzzles. Otherwise I'll never get all of them done. So anyway, that's enough rambling for me. Let me know how you're doing with these, or if you're still playing along at home. And I will see you on the next one.